In this video, we'll look at analyzing a couple of larger circuits where we're also going to model the initial conditions. So here we have a circuit with two meshes. It has two capacitors, two inductors, two resistors, and two voltage sources. So if we're going to write mesh equations for this circuit, we'd have to write two mesh equations. So how should we model the initial conditions in order to do that? We have an initial voltage across each of the capacitors. We're shown the direction of that initial voltage and initial current through each of the inductors, and we're shown the direction of that. And we're given a value. The value is in terms of a variable, so we'll write our mesh equations in terms of these variables. But our first step is to decide how should we model these initial conditions. And if we go just take a peek at how we can model our initial conditions based on our time domain formulas for voltage current relationships, we can model a voltage in series with an inductor, and we can model a current source in parallel with an inductor, or we can model a voltage in series with a capacitor or a current source in parallel with a capacitor. So what we're going to want to do for our mesh equations is we're going to want to model something in series so we don't end up with additional meshes. So that's what we'll do for this circuit here. And so we'll be modeling additional voltage sources. So those voltage sources will end up on, we'll put them on the right hand side of the equation, and on the left hand side of the equation will be our passive voltage. Remember, our mesh equations are KVL equations. But so first we have to convert this to a frequency domain circuit with our capacitances. So since we're going to be finding voltages, we'll represent our capacitance as a capacitive impedance, so where C1 will represent 1 over SC1, and this V1 of 0, we'll model that. We have to make sure we get the direction correct, is our V0, that initial time domain voltage divided by S, and we'll model that so that the positive reference is in the same direction as our V1 reference. Down here, since our V2 of 0 has a positive reference at the bottom, that's where our positive reference of our V2 of 0 over S will go. For our inductors, if you recall, we had modeled them initially. We had said, okay, we'll model that as it's up here, as a plus on the top, negative on the bottom, negative V Li0 minus. And that's, again, how we derived to do that. So when we model this here, we are putting the positive on the top. Why is that the case? Because this current is flowing upward, right? So we have the negative reference where the current is going into, and then we can call that a positive voltage. Our current is flowing into this negative reference, and so from this direction we're calling it a positive reference, because we don't want to have a negative L2 I2 of 0. So once we have those properly modeled, and that's the first thing we have to do, we have to determine we're going to use voltage sources so that we can just write two mesh equations, and then we have to properly model those initial conditions, and then we can write our mesh equations. So writing those mesh equations is not that difficult. Analyzing them afterwards is. But so we're going around and we're summing up all the voltages. So if we go into the negative terminal VA, we're calling that negative, so we'll just put it on the other side of the equation, the positive VA on this side. But all our passive voltages, we'll call those positive, so we have our I1 times R1 plus 1 over SC1, and then this is going to go to the other side of the equation, but we went to the positive voltage reference, so we put a negative on the other side of the equation. And then we have our I1 again times our 1 over SC2. We went into the negative voltage reference here, so when we pull it to the other side of the equation, it becomes positive. And then we have our SL2, SL1 it is, sorry, times I1. And again, we went into the positive reference, so it becomes negative L1 I1 on the other side of the equation. So we did this all in one step. We've done this in a couple steps in the past, but make sure that you understand how to do that. So that's for I1, of course, but now what we also have in this shared branch is we have I2 flowing upward. So our I2 flowing upward in this direction is going to cause the negative reference on our positive, on our passive components, the inductor and the capacitor, is going to be on the bottom, so we subtract them. So if you remember, since we have I1 and I2 on both sides of the equation, our 1 over S2 and our SL1, right? Those are here, our shared references. Those show up. It's negative for I2. It's positive for I1, right? So all our passive references for I1, because of our methodology, are positive. All our passive references for I2 are negative. And similarly, we can go through and write our mesh 2 equation. So hopefully you can do that. And the other check that we have is here we have I1. What we have for our this term for I2 is the negative of this term for I1, because we have these two currents flowing through this shared branch. If we have the values then for our L1 and our R and our C1, we can go through and we can analyze these two equations and two unknowns. We'll look at doing that later. Right now we're just looking at how we model, and we can still come up with these mesh equations. So this simple two mesh equations have a lot of terms of S and a lot of terms without S. So we'd have to, that's how we'd work out our algebra with S. So let's also look at a nodal an example where we want to write nodal equations. So this is almost a single node pair, but it's not quite, because we have this additional inductor and capacitor in parallel. So we really only have two nodes in this circuit, right? We have three nodes. We have this node here on the left, we have this node here on the right, and we have our bottom node, which we'll call the reference node. So if we want to model initial conditions now, we want to limit the number of nodes. We want to limit the number of equations. So we don't want to add additional nodes. So now we would like to add current sources in parallel, and that would not add any more nodes to our circuit. So that's the key here. So if we take our circuit and we model then for our inductor, for example, we model then this current I2 in parallel to L2, I2 flowing through L2. We model it in parallel with L2, and it's flowing in the direction of I2, up in the top there. And then, but for our capacitor, that current C1 V0, that's flowing in the opposite direction. So make sure you understand why that is in fact the case. Then we can go through and we can model each of these. Notice also that we're representing, so this is represented as an impedance, our 1 over SC1, that's the impedance of this capacitor, SL2, that's the impedance of the inductor. But we say this is G, because when we write our nodal equations, we want to find all the currents. So our current is V divided by Z, or V times Y, V times our admittance. So we could have written these instead of writing SL1 in terms of ohms or its impedance, we could write it 1 over SL1 in terms of the admittance with a unit of Simons. So that might make more sense here when we do this, but it's not shown that way. But we can go ahead then and write those nodal equations. So when we write those nodal equations, we have V1 times G1, right, or V1 divided by R1, which is V1 times G1, V1 divided by our SL1, or V1 times 1 over SL1, which is the admittance. And then we have up here, V1 divided by 1 over SC1, so then we multiply by SC1, and V1 divided by SL2. So this is everything, all our passive currents flowing out of the node for V1, but we also have this side, and this side what we really have is V1 minus V2 divided by 1 over SC1, right? And we have V1 minus V2 divided by SL1. That's that current up there. So I've just already separated those, and here this is where we've subtracted those. So we can write our equations where we're already separating our variables V1 and V2. And then we have our active currents, our source currents, I should call them, what's flowing into the node on this side of the equation. So we have what's flowing out, our passive devices, what's flowing in, our active devices, and what becomes active as well are our initial currents, right? So our initial currents, we have IA flowing into to a V1 node, and we have I2 over S flowing into this node, and then flowing out we have our C1 V1 of 0 and our here our I1 of 0 over S. So we've already organized this equation as we wrote this, because we knew we have experience now with our nodal analysis in order to do that. So again, our check, we see that what we're subtracting here, we're also subtracting in the V1 portion of it. That's where these two nodes are sharing the current. And we're making sure we have passive currents out are equal to active device currents flowing in. And what's also an active device, considered a sourcing current, is our initial conditions. So we want to make sure we model those initial conditions correctly, or we'll be subtracting or adding incorrectly. We want to make sure we get the currents in the correct direction. All right, so that's all for this video.